Alright, time for another DraftPhysics.com video presentation. As we appear to be recording, so we don't need that anymore. Anyway, so let's just, where are we here? We can't get any response from people who say they know physics, or certainly the ones who are well degreed in physics will evade the argument. They'll claim you don't understand when they'll seem really stupid in terms of not being able to even interpret the questions. And they're not questions that 9 out of 10 people couldn't understand. They're questions that can be understood by people that have some reasoning skills. So the Dermot guy, I could point to him, seemed very confused by the very idea that somebody would question the kinetic energy formula. Like, couldn't even grasp the concept that somehow it was something other than the most proven theory in the history of mankind. And you get a lot of that on the, like I said, the core of the forum. So they either block you or they, whatever, silence you in some way or other. In terms of getting any response, you can't really put them in any kind of frying pan. They'll evade any kind of obligation to answer. And yet some of these scientist types will make a living mocking, flat earthers and make money doing that. It's pretty tacky. Conspiracy kooks, really. And they're not just kooks, they're obviously malicious disruptors. They just want to disrupt the system. And so they give them attention. The people who actually are seeking attention, whores, that's all they really are, they'll actually give them attention, which, is just so ironic. And yet they'll complain that other people who might be interested in arguing physics are in it for some other reason. So I've offered $2,000, for a good response, scientifically, a well done critique. And in some sense, on a popular enough channel, I don't even care if they critique it. I just want them to expose the idea to physicists and oblige them. The ones that have any integrity will be, logically one would say they would be interested in defending their physics, defending what they believe. It's been challenged. They think they would stand up and meet the challenge. All right, so I've gotten, people complain that I delete comments. Well, I obviously delete rude and stupid. I have a right to. I don't have some obligation to put video links into all the comments section pointing out, well, here, in this video, I answered your stupid question. I read it and answered it, and it's crap. And besides being rude, why it shouldn't be. People shouldn't have to tolerate that. Frankly, no physicist would tolerate it on his channel. So it's, Professor Lewin, inspects all the comments ahead of time. He doesn't allow you to post shit. So there's no double standard. And I've clearly set the invite. If you have some evidence to present or some argument to make, email works just fine. My forum mail doesn't even require you to submit an email address. So, what's the big deal? You can pretty much anonymously, spout your shit, in this sense. And I can honestly say nobody spouted any shit. Jerry Hall for a little while was, posting some counter arguments, but as I pointed out, by reading them and pointing out how they're crap. So we have zero evidence. So in 300 years plus, they haven't been able to produce anything but clay experiments. And any modern inspection of clay experiments will, a modern physicist can figure out if his mission is to find the flaw in this experiment, they'll find that flaw because it's that obvious. And that's all the history has. So this is, it's, again, the theory was first proposed by Leibniz, who was discredited pretty resoundly by the fact that he cheated a lot. He, in arguments, he would change the date on his documentation and do some other trickery to try to say he had precedence on an idea. And then when he was accused of stealing Newton's calculus, obviously those past behaviors came back to haunt him, so to speak, and he did not die in everyone's admiration, let's just say that, where Newton, of course, did. So Newton's physics certainly won in the short term, but then, in the early 1700s, this was dug up again by the French and Germans, and proposed because, again, for suspect reasons by individuals who wish to, support a very life-aggrandizing theories, theories of free will and human, human spirit and stuff like that. New Agers, you could almost argue. And was resurrected with clay experiments. I mean, a tiny, the evidence pool was clearly just quote mined to create a presentation that gave an impression. So it was no better than Ken Wheeler physics. I'll exclude everything else that we know about something, and I'll just show you one little thing and say that this is the proof. And, any good scientist knows you can't, that's just really dangerous and bad behavior. And that's all kinetic energy has to support it. And in the 1800s, it was picked up by Young and a couple other mathematicians who apparently, when they started figuring out that heat is really a consequence of this movement thing, it's just a transference of movement, that they had to clean this up because the kinetic energy formula had outrageous, huge numbers. So they ended up contriving some math that put it in better balance, but it's still the dime going 1,000 miles an hour and the 2 kilograms going 1 mile an hour problem still exists, and that the same event in fact can produce those two things. And it's illogical to say they have, by the event, created two things that have different amounts of this quantity of motion, momentum, because they don't. They have the same momentum, and momentum is energy. So anyway, so contrived math that just kind of shoots in the face of Newton, in the sense that they took Newton's simple statement that if you want to know the force acting on something, you just figure out how the momentum changes. The change in the momentum is the force that acted. It's that simple. And they perverted it into this, again, 1/2 mv squared that has, you look at where does that come out as something so simple? So Newton says change in momentum equals the force, and they turn that into 1/2 mv squared. How do you get that complicated out of something so simple? It's almost, they've taken something elemental and said the elemental function is something much more complex, which they do all the time. But anyway, right, so that's the background. So I just thought I would go over the argument for momentum being the only reasonable way to look at what goes on in the universe, and the fact of why clay experiments are just fundamentally flawed in terms of penetration in clay being the way you measure how much energy something has. So, as I've attempted to state, there's just something moving, a mass that moves. And so you're really just saying it's got a quantity of motion, Newton would say, and that really just means a volume. So the volume is either going to be, you have a little bit of mass and a lot of velocity, or you have a lot of mass, okay, really not the same size, but close enough, and very little velocity. And so that's just the way you can shape something as simple as your quantity of motion. So you can be a heavy thing, lots of little soldiers marching slowly, or you can be a few soldiers running very fast. And the fact is those two things can push the same amount of stuff in the universe. In terms of which your outcome is you want little bits going 30 miles an hour, let's say, right? You want little bits going 30 miles an hour as your outcome. And it really doesn't matter if you put one bit in going 900, okay, so you have one bit going 900 miles an hour, or you put, you know, whatever, 40 little bits going 30. You know, I didn't do the pre-math, but I'm just saying it's just a quantity. It's just a volume. It's just a volume of, you know, mass times velocity. That's all there is. And so in an interaction, when things interact in the universe, that is, stuff has to go through stuff, like you have to move through atmosphere, or you're going through a substance. All you're doing is exchanging the little soldiers. You're just saying, I have a certain number, and I can, you know, make a deal, so to speak, and make exchanges with something else. You blend your stuff. Well, exchange is the better word, because see, the stuff has a direction and it wants to keep going in that direction, so it just jumps into the other object because it's already going that way, right? So you're just giving it a path. Like electricity, once you hit something, you're just giving the energy a path to go into the other thing, and now it's not in this one anymore. It's not trapped in this one because now it has a path out. And the same goes for this. This one says, I want to get rid of my stuff's going this way, and so it still wants to go that way, and so it goes right into this other object because you've made contact with it. And now the pressure, the soldiers can move through, you know, they can go across these bridges you're creating through contact. All right, that's one way of understanding it. All right, so as I've pointed out, you know, when you do, so we'll go one step further. You know, they do vector math, and the idea is if you want to add two things up, well, you just measure the direction is one thing, and then the velocity is the intensity of something. Now, you could do it with just the momentum. You could say the arrow represents the momentum, that is the mass times the velocity. Or you can just do velocity. So for the sake of the argument, we'll just do velocity. And so you have two things doing two different things. Well, the idea is when you add those things, you put this arrow on that arrow. Not exactly perfectly done, but close enough. And what you get as a result, this is your byproduct. And so you can sort of understand that the longer arrow will control the new arrow, the product arrow. The product arrow will be controlled by whatever one is longer. So you can sort of understand that when something crashes into something else and it has high velocity, that the product, no matter what it hits, is likely to have this in it. It's going to have this direction. All right, it's going to keep the velocity going in this direction. So it's going to transfer, okay? It's going to make contact with something. The contact is going to keep the energy moving this way, which means that the new object, the object you transferred with, is going to essentially just go in the very direction you're going, in something close to it. And by going in the direction you're going, it means it's going to have contact with this thing here. So instead of you having to hit this, it will hit it for you, which means you really kept your energy, right? Because your momentum is still working in the same direction you're going. So obviously fast things will tend to keep pushing things forward. So instead of, like if it was bowling pins or something, the faster you hit them, the more likely they are to go straight. And that means they're going to keep hitting each other, and they're going to just plow the road for you. So that's why something going fast hits clay. Its energy really stays in this direction. But if it's going slow, it means that when something has a competing arrow and it's got the same size arrow, the problem is when I put these two arrows together, I get this. You know, I get something way off of what I originally had. I mean, you know, the product isn't going to be in the same direction I'm moving. And so when things make exchanges at slow velocities, the environmental temperature, that is the speed of the stuff you're hitting, is going to have arrows that are going to be a lot closer to the size of your arrow. And that means the product is going to be something much more divergent off your path. And so instead of moving your energy, keeping your energy going in this direction, your energy will start spreading in these directions. And that's why some materials are better and worse at measuring energy. So as I've also pointed out, I mean, a physicist would know that, well, clearly clay is deforming, reshaping, based on this principle. And it's also doing it on, by tiny little atoms moving distances and moving around. So the atoms can actually move this way and then move back this way and do all kinds of deformation that won't have any permanent, it won't reveal what really happened, which was energy did go this way and it did go this way and it did go this way and it did go this way, this way, and ended up back at the same location. So if you look at the clay after, it could look just like the clay before, but really you did send a bunch of energy out this way, and that means you shot energy that way, and that means you shot energy that way. And so you gave the environment your energy in terms of a bunch of inelastic movement. That is, you vibrated, and the vibrational energy went into the atmosphere. Obviously, if I move my hand this way, I push the atmosphere that way. Move my hand this way, push the atmosphere that way. So I'm losing the energy to the environment by moving. And so if the clay jiggles, okay, then you can lose a lot of the energy, and you won't see it. When you look at it later under a microscope or something, hey, it's in the same place. Didn't move. Well, it actually did move, and it did transfer its energy to the environment. You just didn't see any of it. So it's not a very good way of scientifically analyzing or dissecting energy. Where something like a spring, okay, as pointed out, does a very reliable thing. It's very hard metal. It's doing the little magnets moving. The atoms are moving. The atoms have a comfortable place to be in. Well, you could probably better realistically say it's like this. Okay, so when the atoms are in their lattice or their matrix, they have a position that balances them. And obviously when you're bending the steel, what you're doing is stretching one side and compressing the other side. So you're moving, you're changing this arrangement into something like this, okay, where now there's an imbalance. So now you've changed the balance, and this is more repulsive. And so you're building up tension inside of the atoms that will, like magnets, they'll just try to get back to their comfortable place. So as soon as you give them an opportunity to push back, they'll push back as soon as they're free to do so. And so the spring stores the energy. So it's a storage device. Now, a storage device is going to be much better at telling you how much energy there is because it's actually storing the energy. And if you know it to be an efficient storage device, that is, I push in with a certain amount of mass at a certain velocity, and I push it and compress the spring and lock it. If it gives me back almost the same amount of stuff, tiny losses, 0.001% losses kind of thing, tiny losses. So the spring is proven to be really, really conservative in that it doesn't do a lot of environmental work, and it doesn't lose the momentum by causing a bunch of other things to move. So it does this, this is probably an exaggeration. But it will do pretty well. If you can create a slick track between two springs, a frictionless track, it can go back and forth for quite a long time before the spring's inefficiency, degrades your energy. So what you put in comes back out. And so it's been proven, well established, that this device works. And so what the kinetic energy formula creates is this silly paradox where I compress a spring, a certain amount with a certain amount of slow pressure. So I take a heavy mass, okay, and I push it into the spring, and I get it to go to a certain level based on the fact that the pressure will essentially be the weight in this direction. I'm going to give this mass weight by applying pressure, velocity. And there'll be a certain place that it'll compress the spring to. So it's going to create a certain amount of energy in the spring. And then all I would have to do, and it has a certain joules of energy, we'd say. We'd say the momentum of the object going in, let's just, say it had a mass of 10 and it had a velocity of 5. Kinetic energy tells you that, you just do 10 times 5. Well, you do 5 squared Okay, so that's 25. Times 10 is 250, and then 1/2 of that is 125. So that's how much energy, that's the volume of energy they claim to exist. Momentum just says you have 5 times 10, you have 50. And then I would multiply that by 2.4, I can't remember the number. But somewhere around 3 even, 2.7, yeah, maybe it's around 3. And then you get 150, but that doesn't matter. Let's just go with 100 for the real number. But anyway, just do the 2 thing. Don't want to get off the course. Okay, so this is the kinetic energy. They're saying compress the spring. So they're saying there's 125 joules of energy here in this spring. But the fact is, if I put this, I put a 5 kilogram object on there and then release the spring. Okay, so I'm putting it back here because the spring is now compressed. Well, I said, not an important detail, but whatever. Alright, so I put a 5 on there. Now it's only got a 5 mass, and the fact is it's got a certain amount of compression that produces a reliable amount of energy. And the fact is it's going to leave a 10 as its velocity. So it's going to be the inverse of this object. This momentum is going to be conserved. So you're going to get the same momentum number. And the momentum number was 50 as the number before the conversion. So you're going to get 50. So 50 is what's going to come out in terms of momentum. But they say the kinetic energy, right, because now that I've just switched the numbers, I've got a 5 mass and I've got a 10 velocity. So now I square the velocity and get 100, and then I multiply that times 5 and get 500, and then I cut that in half and I get 250. So somehow I converted 125 joules into 250 joules by just putting a lighter object on the spring. And this is what every piece of physical evidence indicates. This is how springs work. They conserve the momentum. So it doesn't matter what size. I put a dime on here. I put a 0.002 kilograms, or I put 2 kilograms. 1,000 times more weight. Doesn't matter which one I put on here. I'm going to get the same momentum out. And that's the truth of the value of springs, is that they're very reliable. Now, they have tolerances. They can't go faster than the steel, the metal, the weight of the mass in the spring can produce. So heavy springs that can take lots of compression, lots of joules of energy, can't move as fast. Just a fact. So they're not going to be able to give things their portion of velocity. So there's limits to how far you can go with these experiments. And obviously you can break springs. You can move them so fast they crack, or you can pull them apart so far that they stretch permanently and they won't give you back energy anymore. So you can break springs, but they have a very good working range. And the simple truth is this number doesn't fit with this number, doesn't fit with that number. It's incoherent nonsense. Now, when this is a different circumstance, they'll say that, somehow, the environment did it. They'll blame the nonsense of the numbers on some event that they'll say we just didn't see. So in the example of, taking 2 trains and banging them into each other, let's say, combining them, coupling them. So you have 5 mass here and you have a 5 mass here, and you move this one into this one's not moving and this one is moving, okay? And so you have a certain amount of velocity. Let's say you got 10 times 5 as the momentum, and that's an understanding of the velocity. 10 velocities, 5 mass. And now it'll be spread over a larger object, so when they're combined, it'll be a 10 mass. And the fact is, because momentum is conserved, it's only going to be going 5 velocity. So it'll lose half its velocity because it's doubled its mass. Now they'll make up a story that half the energy, half the joules, half that 125 joules somehow disappeared. Well, the 125, right, because it's really 250. Okay, so this one has 250, and it's going to go down to 125. they're going to argue that somehow there was all kinds of environmental changes and all kinds of stuff. But no, you can do this very efficiently. You can couple these cars very efficiently, or you can drop the weight right on top of the car. You know, it goes by and you just drop the 5 tons on it. So there's lots of ways you can add the weight. And we know those ways of adding the weight are not destroying the momentum. So how exactly can you create the heat? So we're back to the argument that if you're going to make heat, or deformation or anything, it has to come out of your momentum. So if you're moving and then you're hitting something, air or water or a frictional surface, no matter what it is you're hitting, you're making an exchange with. So friction is just you hitting matter and giving matter momentum. So you have to give what you have. So if I give this a vector, it has to come out of me. I have to take it out of my volume. Okay, so if I give this momentum, it has to come out of my volume, my quantity of energy, my quantity of motion. And if I hit this bit here, well, that has to come out of my momentum. That has to come out of mine. So I either lose my mass or I have to lose my velocity. Now, obviously, things don't lose mass, so it's always just going to be about the velocity. So my velocity is 10, and I gave 2 velocities to this, then I only have 8. All right, and so when I hit this next object, well, I only have 8, so I can only give it, 1.5, let's say. And then I'm going to be down to 6. And by the time, so as I hit the things, I'm losing my momentum. So if I'm making deformation, that is, I'm changing the position of atoms, or if I'm making heat, that is, I'm causing atoms to just move around, the movement had to come from my movement. My movement had to put its energy, its soldiers, into something else, and I don't have them anymore. So I can't possibly, by the time, if I'm doing all this deformation in the process of interacting with something else, and I'm sending all this crap going in different directions, I obviously can't transfer my energy to the other thing. I can't conserve my momentum, give it the same momentum I had, the same velocity I had, the same amount of power. I can't transfer to this and do all this other work in the environment. It's just ludicrous. Now this can do it, right? I can hit this, give this one 100%. Like I could have connect balls. I could have this other ball flies off at, one ball goes in, the other ball goes out, and this ball stays. This one has 100%, and it can do 100% work here because it has 100% of my energy, so it can do 100% work. Well, if I only give it 50%, you can understand that I could still have my 50%, and the 50% it has can still be going in the same direction I'm going, so it's going to take care of stuff that's in my way, in the sense that it's going to give it momentum, so I'm going to have a free ride. So that's why velocity beats friction. That's why velocity allows you to penetrate clay. It's because the thing you gave your motion to, you didn't give it in this direction or this direction, you gave it in the same direction you're going. And it's just plowing the road for you. So you're getting a free ride because you gave the energy to somebody who's working in the same direction. The work is still being done in the same direction that you're going in, the work. All right. So I've been over all this before, but I just thought it would be good to say it again, maybe better. So, so we're at a standstill, I guess. I guess I'll just go back to some other subjects, or maybe I'll just take a break. Maybe I'll write some stuff, who knows. But I can't buy an argument. I mean, it really is that bad. They're that cowardly. I can't. I asked them how much do I have to pay you? AB Science. I've asked them, how much do I have to pay you to grow the balls to do your debunking, to prove that something in this video was ludicrous and nonsensical? How much do I have to pay you to demonstrate that your science has an answer to these problems? To show it. To show something, okay? But, all he'll show is a mathematical equation. He'll just do a derivation. He won't show any evidence. He won't model anything. He won't explain it by explaining how you heat the environment and 100% transfer your momentum. How is it possible for me to heat the environment, cause a bunch of movement in the environment, and transfer my momentum 100% to something else at the same time? You won't answer the question because it can't be answered because it's not possible. And the physics is nonsense. The history is terrible. They won't even own up to the bad history. They won't acknowledge any of this is doubtable. Yet it's so overtly and obviously doubtable. It's so horribly flawed and so illogical. And yet we get nothing. And, that's just bullshit. I'm saying it's bullshit. Half-hour warning there. Anyway. So that's enough. You guys really don't. There's no counter argument. There's no counter evidence provided. There's no counter reasoning provided. And, nothing. And they really don't even want to talk about the mathematical derivative in the sense that it does require you to get into precisely why they create these exchanges and say there's equivalencies. And as I've pointed out, the key one for some of the derivatives is they're just converting distance into velocity. It makes sense to multiply a velocity times a distance. It doesn't make any sense to multiply a velocity times a velocity. That doesn't make any sense. If you want to know how much a force is affecting something, understanding that if it's got to constantly maintain the velocity, then the force is constantly changing the velocity or something like that, then you would add it up. But it's really, it doesn't make any sense when talking about exchanges, because we already know the quality or the quantity of the motion is something it has, and it's going to keep moving unless it does exchange with something. It's only through exchanging that you can lose your velocity. So if you're in space and something pushes you, you're going to keep going because you don't lose it until you interact with something. Now the electrons and protons are interacting, so they will lose theirs. But as long as they're in the form of matter, they're in an arrangement that's that recovers their velocity and maintains it. So large objects will just keep going in space. So even distance is irrelevant in the circumstance of objects that aren't being pushed by a constant force. Alright, anyway. They aren't fighting some constant force, in fact. But anyway, enough. So, yeah, we'll call that a video. So this has been a DraftPhysics.com video presentation. Until the next time and such. Not much I can do. I can only make reasoned arguments, and all you people apparently can do is make unreasonable, nasty, ad hom attacks against me personally. So, yeah, you don't have anything. Nothing. Oh, wrong button.